This is a recording on the Western Indian Ocean and refers particularly to the growth of the small Somali Plate and the Indian Plates. This is a picture of general plate distribution. You'll notice in particular, with reference to the African Plate, that there's the western section, the Nubian Plate, which is most of Africa over to the East African Rift. And then the Somali Plate is added to continue to the centre of the Indian Ocean. Somali Plate is often included with the African Plate in broader discussion, but it's clearly separating, as is seen from the Great Rift Valley extending from the Red Sea down west of Lake Victoria and finally down to the Antarctic separating boundary. Its eastern boundary is the central zone of the Indian Ocean proper, with the Indian-Australian Plate also shown here broken up. And more recently, it seems that red line is a new plate boundary developing between the Indian Plate and Australian Plate, although we've moved together significantly until 20 million years or so, when India's had this impediment of the Eurasian Plate and has developed the enormous crumpling of the Himalayas. You'll notice also between the Somali Plate and Africa, there's a series of grey areas. There's a Madagascar Plate, which is effectively extinct today, and extensions of that into Tanzania. This is a look see at how plates develop, really. The Somali Plate is breaking away from the Nubian African Plate along the series of rifts that straddle Lake Victoria and go up to the triple point at the Gulf of Aden and the Red Sea boundary. There's other indications of boundary cutting across to Madagascar from Tanzania. It's nevertheless effectively a plate bounded on all sides, that's speaking of the Somalian Plate, bounded on all sides by divergent boundaries. There's no subduction involved on that particular plate. The origin of new plates in continental areas is best illustrated by the East African Rift, where fractures have developed over a domed region that results from convected heat in the asthenosphere. So the plates, which are nearly 100 kilometres thick, of course, are rifting and separating. Here's the process of separation. You tend to get central rift, where Lake Victoria, for example, occurs, a general doming, so the shoulders of the rift stand high. Overall, a doming region, so there's tension at the crest, and the wedge-shaped block drops in the central rift region. That's referring to continents particularly, and you can see how the convection cells are adding the heat underneath as they come up and spread out to tend to draw the plates apart and permit the generation of magma at a depth of about 100 kilometres and its intrusion as volcanoes in the central rift. The three plates of type boundary, and this is really the top of the three shown on the right-hand side, it's a divergent boundary, and the second type are the convergent, where there's compression, and in this particular case, the oceanic plate would slide in underneath continent or ocean plate, giving you subduction. And of course, if it were continent meeting continent, it would be a thing like the Himalayas with considerable mountain building, because neither plate essentially wants to descend into the mantle. The third plate boundary type is the transform plate boundary, shown at the bottom of those three on the right, where the plates just slide past one another. And reading this, there are three types of plate boundary, two of which, divergent and transform, are apparent with the Somali Plate of Western Indian Ocean. There's no convergent plate boundary involved with this plate. Of course, there's a fundamental difference between continents and ocean crust. Ocean crust produced by volcanism from the central spreading ridge is only about 8 kilometres thick. It's basaltic, it's dense. It's very little differentiated from the underlying crust and mantle of the Earth. The continent, on the other hand, is much more silica-rich, lighter rock in general, including a lot of sediment, often 50 kilometres thick, varying perhaps 30 to 60 kilometres. The plates overall are about 100 kilometres thick, so that the underlying mantle is sufficiently lithified to be portion of the moving plate, and the convection current occurs lower than this. Looking at the Indian Ocean, we can see India itself up there at 2 o'clock, Arabia at 11 o'clock, and the western part of the Indian Ocean is lying on the Somali Plate, because the red line running through centre or slightly right of centre of this diagram is the spreading ridge from which the Indian Ocean has expanded over the last 80 million years since the separation of India from Madagascar, which occurred about 80 million years ago. See a scale for 1,000 kilometres there, near just extending from the coast near Somalia. As I said previously, the Somali Plate is surrounded by divergent boundaries, and those are the red lines illustrated here, exception of the Red Sea running up at 11 o'clock. It's incomplete, of course, doesn't show the East African Rift or its connection with the Southern Ocean boundary to Antarctica, but the northern tip of Madagascar is evident, plus various plateaus that sit off to the north, including the Seychelles Islands. The Seychelles are actually a mini continent, in effect. They were derived at the time Madagascar separated from India. But there is also an anomaly in the great ridges that extend down from India through the Maldives, and the southern extension of this, which goes beyond the diagram at 6 o'clock, the bottom of the diagram. So the West Indian Ocean involves the broader African plate, which is comprised of a Western Nubian plate, the main mass of Africa extending across to the mid-southern Atlantic, and the Somali Plate, which includes the one-time Madagascar Plate. And the Somali Plate reflects the growth of new oceanic crust in the West Indian Ocean over the past 80 million years, as in fact does the Indian Plate, which has the mirror image. And the boundaries of the Somali Plate are extensional. In the east, they're oceanic spreading ridges, and new oceanic crust is forming here. That's as India moved northward, the plate on which it lay tended to close oceans to the north, the Tethyan oceans, which existed for several hundred million years in the Eurasian region. If we look back a couple of 100 million years into the Jurassic period, age of dinosaurs, it shows how things looked in the supercontinent Pangaea. Madagascar was lying against the west coast of India. This is relative to East Antarctica, and the various lines across the continental masses are the present-day Latin longs, which only gives you some indication of where they are today. Madagascar is shown up significantly further north against Tanzania than it lies today. And the Seychelles are evident there near that red circle, and they clearly had their origin at the time of separation of Madagascar and India, which was only 80 million years ago, compared with the earlier separation of Madagascar and Tanzania 120 million years ago. I think the only comment I'd make here that Sri Lanka possibly lay a little bit closer to the point of India at that time, maybe even around the corner, slightly nearer to Madagascar. And it has moved relative to India a little bit to the right in this diagram. Reading this, it's Gondwana, This is how things looked in the Jurassic 200 million years ago relative to a fixed Antarctica. Madagascar drifted away from Africa 120 million years ago, but split from India only 80 million years ago. And I also comment that as recently as 66 million years after the start of separation of India from Madagascar, and probably after the independence of the Seychelles as a mini continent in the middle of ocean, you had an enormous plume of heat come from the outer core of the Earth some 3,000 kilometres down, and it formed huge volcanic features in India known as the Deccan Traps. That suggests or indicates that India at that time lay over the hotspot, which today is volcanic Recherche Islands, which lie to the east of Madagascar. So there is a story to tell in the bedrock of the West Indian Ocean for the migration of India as a result of its movement across that hotspot, which has been stationary for 100 million years and more. This is a very colourful rendition of the modern situation. This is a modern geological or tectonic map showing the ages when rocks were formed. And this shows the Somali Plate, surrounded again by a red line. The entire plate is visible here. So Africa, with all its maroon colours and brighter pinks, are all older than 1 billion years, for example, as is the eastern section of Madagascar. And India, likewise, except India has a big patch representing the volcanics in a bluish colour or tealy colour. But that's the volcanics of 66 million year age. But if you look at the main eastern margin of the Somali Plate, we see how the laminae or the layers of oceanic crust have been added, starting with green at 80 million years ago, brown at about 60 and orange 30, and the yellow is only 10 million years to the present day, which are quite symmetrical with the opposite bands on the Indian Plate. It's because that central ridge has been separating continuously, and the plates are being pulled apart by the convection currents moving India north, and effectively Madagascar somewhat to the south, I suppose. You have this characteristic mirror image of the Central Ocean region as young as 10 million to, or as present day, to 80 million years ago, which was the main separation of India and Madagascar. One can also see the blues and greens between Tanzania and Madagascar. This is a plate that's not really active today. It's a separate plate set in there. You might call the Madagascar Plate, but it represents the separation of Madagascar and India with it at that time from mainland Africa. Reading this, this shows the age of rocks and oceanic crust of the Western Indian Ocean, or entire Indian Ocean really, except Australia is not present here. And Madagascar had separated from Africa by 120 million years ago, but that particular plate shown in blue and green is part of the Somalia Plate today. And India and Madagascar didn't rift apart until 80 million years ago. So the oldest oceanic crust between those two continents effectively is shown there in green, with an indication of, in black, of 80 million resting against it. And the symmetry of the ocean floor ages across the mid-Indian Ocean rift illustrates the spreading or growth of the Somalia and Indian plates at their central ridge over this interval of 80 million years. And how do the plates grow? Well, this is an indication of the formation of new basaltic ocean crust at a mid-ocean ridge. It, of course, results in the spreading of the ocean floors and the ultimate separation of the plates. Tried to indicate here in the edge-on section some of those colours that indicate 10 million years, the yellows, and getting to oranges at 30 million years. Crust, oceanic crust in both cases here being 8 kilometres or so thick, and the plates themselves about 100 kilometres thick, at which depth you had the magma developed and its intrusion into the mid-ocean rift where the plates are separating. So this is typical of a divergent or constructive plate boundary, constructive because new crust is being built here, and upwelling magma continuously feeds those separating plates, which is separating being driven by convection currents. Draw the comparison with sugar syrup and convection currents coming from the heat in the centre of the pan, tending to spread, separate and add new material at the centre. Any scum tends to get moved across with the plates, collecting on the side as continents ultimately. Hence, they're carried quite passively on the moving plates. Here's a Google Earth image of the western portion of the Indian Ocean. We can see Madagascar down the 7 o'clock position, coastal Africa running north to the Horn of Africa, the Red Sea running away towards the Mediterranean at 10 o'clock. Now, up at 1 or 2 o'clock, we have the Deccan Traps. This is the huge volcanic area of 66 million years ago, and there's a ridge trending directly south from that to the Maldives and ultimately to Point Marianne. And that is the trail of extinct volcanoes that have developed over a hotspot. One would normally expect it right down near Point Marianne, but there is a complication here because that trail of hotspots, liken as you will to the Hawaiian chain of seamounts, is actually related to the run that ends at Reunion today and through Mauritius. That trend running northward in the bottom of the diagram at 6 o'clock is also a line of extinct volcanic seamounts, except for Reunion, which is the active volcanic point above a hotspot today. So the plates have moved across that, including the central spreading ridge at some stage or other. And this has separated Point Marianne from the Mascarene Plateau. Now, Mascarene Plateau and Seychelles are actually mini-continents. They're not part of this story of the hotspot track. Reading this, the West Indian Ocean has a central spreading ridge that comes from the Arabian Gulf, extends to the triple point separating the African, Antarctic and Australian points, which is way down at the bottom at 5 o'clock. The notable features of the West Indian Ocean are the submarine plateaus that include the Mascarene in the north and the volcanic trend that is Mauritius and Reunion on it in the south. This latter is the result of plate movement over a hotspot, as I mentioned previously, and it's related to the submarine ridge extending through the Maldives to the 66 million-year-old Deccan Traps of India. Reiterating the Western Indian Ocean, the eastern half of the Somali Plate oceanic crust has grown from continued spread at the volcanic rift at the central ridge of the North Indian Ocean over the last 80 million years. The western half of its ocean floor appears to be a former plate of older crust that resulted in the separation of Madagascar from Africa 120 million years ago. It's the western half of the Somali Plate. India was then still attached to Madagascar, and that separation only occurred about 80 million years ago. And the plateaus of the West Indian Ocean are of two origins. One series is due to a global hotspot, the Reunion hotspot, which is a large igneous province. It shows a track of submarine extinct volcanoes which effectively run north to India and the Deccan Traps. And the Seychelles, however, are an exception. They're a microcontinent that owes its origin to the split of India and Madagascar 85 million years ago. Looking again at a zoom image of the whole of the Somali Plate on this occasion, we can see a separate sort of Madagascar plate, which is now, I think, securely frozen with the Somali Plate, so that we look to the East African Rift as the western border of the Somali Plate, and the spreading ridges between the major, called the major overall African Plate, the Antarctic Plate, and the Indian Plate are the eastern boundaries and southeastern boundaries of the Somali Plate. And enclosed within that is this microcontinent just under the word Somali Plate, which is Seychelles, and it had its origin up there between India and Madagascar. Well, not up there, but down there, nearer to Madagascar, when India had not started its journey by the opening of the Indian Ocean. Rather hidden and abandoned boundaries define a Madagascan platelet, which seems to be inactive today. But what is active is the Impression Piton de la Fournaise, the volcano eruptions on Reunion, which are resulting from this hotspot, which is acting like a blowtorch, emanating as a great plume of heat from the liquid outer core of the Earth, coming entirely through the mantle, forming, no doubt, a lava pool at the base of Crust, and periodically or almost continuously erupting at surface. Last 2 million years, Reunion has appeared above sea level and is a very active volcanic area today. And this is the process. So from something of the order of 3,000 kilometres down from the Earth's outer core, you have a blowtorch-like heat plume, which is affecting the bottom of the plates, creating magma, which is rising. In this case, we've got Hawaii written beside it, or we could call that a Reunion in this case, and that gives rise to the active volcano, or volcanic centre. But of course, the plates are moving across this. They carry the edifice of the volcano away from the heat source, and you get a line of extinct volcanic seamounts, undersea mounts, extending away, indicating the direction of movement of the plate in past times. Obviously, if you can date those volcanoes, you can tell how much movement there's been from the hotspot in that period. Well, this gives us a quick look at a section through Earth and the difference between a hotspot volcano emanating from this heat plume way down in the outer core, which is liquid. The inner core is solid due to the enormous pressures, essentially nickel iron. Heat is transmitted up, acting like a blowtorch on the underside of plates, creating a magma pool, which gives rise to the hotspot volcanism. In contrast, subduction volcanism is due to an oceanic plate descending under the frequently continent, but maybe also under another ocean plate, giving rise to either a volcanic arc in mountains on continent or an oceanic volcanic arc where ocean plate meets ocean plate. And so there's a distinct difference between the hotspot volcano and the subduction-derived volcanic features that surround the Pacific, for example, in the Rim of Fire. And the writing here says that hotspots are heat plumes from the outer molten core, unlike the shallow subduction, which is related to subduction of oceanic crust and giving rise to the volcanoes of the Rim of Fire. Here's another illustration of the Hawaiian seamounts and the extinct volcanic features, Maui, Oahu, and Kauai, the oldest of those features of the Hawaiian group, which result from the plate moving off towards 10 or 11 o'clock in this diagram and carrying the volcanic edifice away from the zone of magma formation or the fixed hotspot. That's well known to apply to the Hawaiian chain and the emperor chain of seamounts. They get increasingly older as you move away from Hawaii, and they're quite extinct. So most are subsea still, but here are a list of ages in millions of years. So the oldest, Detroit, up there disappearing under the Aleutian Island chain, is something of the order of 80 million years, MA being million N. Whereas if we look at where the bend occurs, Daikakju, at 42 million years, and that indicates there was some significant change in the direction of plate movement at that time. And that's about the time India collided with Eurasia, of course, so may well have been a major series of reorientation at that time. Midway Island there is shown at about 28 million years. And reading this, the Hawaiian and emperor chains of seamounts are extinct versions of today's active volcanoes over the Hawaiian hotspot. Movement of the Pacific Oceanic Plate across the fixed hotspot reveals both the direction and speed of the Pacific Plate growth. Clearly you get the speed if you get the age of the rock, and you can tell the difference between the age and the present and measure the distance it is from Hawaii. That will give you an indication of the speed of plate growth. And 42 million years ago, movement direction changed from northwesterly to west-northwest at that time, as it is now. So if we look back at the plate movements of the Somali Plate, about 66 million years ago, the time of the great extinction on Earth, you had this enormous production of heat on India. And at that time, the volcanism occurring in India was due to the continent lying above this Recherche hotspot, which it's considered has not changed position over this period of 66 million years. So that's the oldest record, and it's occurring on the Indian plate. Separation has already occurred at 80 million years from Madagascar. So there's an ocean there wider than the Red Sea is today. India is about to make very rapid movement northward. It's interesting that this is probably about the time that the Seychelles Islands separated, but their geology is more like India, or perhaps northern section of Madagascar. They're much, much older than 66 million years. They're really portions of the ancient cratons of the order of 1 billion years or more, because they're broken off section of continent. So here is India 65 million years ago, if you wish, 66 million years ago. And you'll notice how this black area is the enormous spread of volcanics of the Deccan Traps, with a reunion hotspot marked in there. A large crater, the Shiva crater, presumably of volcanic origin, and the separated Seychelles island group, which is continental crust, separated from India and possibly also Madagascar. So Reunion Island is attributed to this mantle hotspot, which first created the Deccan Traps when India was in that position 66 million years ago. The Deccan Traps are a large basalt province in India, probably responsible for much of the extinction on Earth at this period, when 80 or 90% of species died out. There was, of course, also a large extraterrestrial impact in Yucatan Peninsula at about this time. And this may have preceded the impact. It goes on to say that the present direct trace of the volcanism extends to Mauritius. Reunion became active about 5 million years ago, reaching the ocean surface about 2 million years ago. And it's the youngest island originating from this hotspot that is still active. Amazing volcanic features of the Deccan Traps illustrated here from India. Just amazing volume of extrusive basaltic rocks. Looking at the trends of these seamounts, it's clear Deccan Traps, around 66, 68 million years. And then as you move southward along that track of seamounts, their ages decrease till Chagos at 49 million years ago. Then there's a gap or a jump to Sao de Malha, which is due north of Reunion and separated by more recent opening of the central ridge. And that dates from about 47 million years ago. The new crust of West Indian Ocean formed and separated this line of extinct volcanoes so that all the younger ones are actually on the opposing side. It's clear that about 47 million years ago, the plates must have crossed over the hotspot and transferred it from the northern section, the Indian Plate, to the Somali Plate. And it has continued, that has continued to move northward and create Nazareth 30 million years ago and Mauritius about 8 million years ago. And finally, Reunion is the hotspot today. So the mid-ocean ridge, I'm reading it now, appears to have crossed the hotspot 47 million years ago. That means the plates have been moving across that fixed position of Reunion, and that's how far that central ridge has moved in a period of 47 million years, from Reunion itself to about where the black arrows centralise. Ocean spread after the 47 million year crustal age carried on since it crossed over the hotspot from south to north at about 47 million years ago. So here then are those notable features again. The submarine plateau of volcanic rocks, essentially due to the result of plate movements over the hotspot and are related to submarine ridges of extinct volcanoes. Now they extend from the Deccan Traps, their oldest, down to Point Marianne, at which point there was a crossing over from south to north of the plate boundary. Therefore, the hotspot appeared on the southern side, but not right at the central ocean ridge, because since the period of 47 million years, there's been new ocean spread those 2 points apart, Point Marianne and the edge of the Mascarene Plateau. And from that time onwards, 47 million years, you've had that trend of extinct volcanoes or subsea seamounts running down to Mauritius at 8 million years and Reunion in the present day, which is where the hotspot is actually and has been located throughout. The Seychelles, a lot of that western portion of the Mascarene Plateau, and the Seychelles are, of course, continental crust. It's not a very clear diagram off the web, but you can see the Deccan Traps up in India at 12 to 1 o'clock, age of 65 million years, Maldives at about 60 million years, Chagos about 48, and then there's jump across the mid-ocean ridge to the extinct volcanoes of 45 million years and 35 million years on the edge of that plateau, running southward to Reunion in the last couple of million years. reading that. The Seychelles Island group is continental crust, and their age is 750 million years and significantly older than that. Dislocation of the seamount chain at 47 million years is due to the central ridge crossing that stationary hotspot, which is located at Reunion. If we look at Seychelles, which are not necessarily part of the hotspot story, Seychelles are a microcontinent, essentially 700-million-year-old granitic rocks for the most part. They're related to the rift of Madagascar from India 80 million years ago. But in the Seychelles, there are rocks of that age, 61 to 67 million years, when the Deccan Plateau was emplaced. Nowadays, the Silhouette and Ile du Nord islands are rocks probably related to that hotspot at the time the Seychelles was separating from India. Clearly, things would have been pretty hot underneath as a result of this large igneous province, which I've marked as a red circle in the second diagram, around 60 million years. And the red spots in each diagram tend to show the presumed fixed location of the Reunion hotspot. And there were emplacements of rocks at about the time of the hotspot, which indicates it was located pretty close to that prior to 60 million years. Red spots show the fixed location of that Reunion hotspot. So if you check it out, particularly in diagrams B and C. But 47 million years ago, the spreading ridge crossed the hotspot, and since that time, the spreading of new ocean crust at the ridge has moved India rapidly northward. Here's a series of positions for mid-ocean ridges, volcanics emplaced at those times, and it gets a little difficult to unravel. It's like skeins of wool, all confused with one another. It's rather an interesting diagram. Of course, a lot of Australian Indian plate has been subducted beneath oceanic material in those grey areas, which has been the closing of the Tethys oceans. Hence, there's been significant northward subduction along the Indonesian island arc as we see it today. Closing now for a question time. Thank you.